Okay, right. Okay, so the first one, well, you probably know both of these things already, right? You know what connectivity is. We just talked about a little bit. And you know what electricity is, I guess, a little bit. I don't really know what electricity is, but I've been around it for a while, so I have some intuition, I guess. I was not a physics major. Okay, so last time we did some of this. Okay, oh, here's a fun one. Okay. Uh, all right, this is just to get warmed up. So undirected connectivity, right? Give you an undirected graph, two vertices A and B. Uh, can A get to B, right? We often do BFS or DFS or something. Okay, so here's a maze, uh, and the rules are uh, you're trying to get from the starting yellow cat to the ending white cat, and you have to like alternate between a face forward cat with like eyes and a backwards cat. There's no eyes. Forwards, backwards, forward, backwards, forward, backwards. And the question is, can you get from start to end? Okay, which is the ambiguous cats? Okay, so you're worried about this cat? This one? Yeah, absolutely. They're overlapping each other. This seems to be not connected. It's all deterministic and it doesn't work. What do you mean? There's obviously like more than one ways initially you can like move around, right? Oh, you start the goal. Okay, remember there's exponentially many paths, so it's really hard to. Okay, there's one way, you can keep going, right? Okay, so everyone feels like it's impossible? Anyone find a way? Anyone want to bet? Huh? No, you cannot draw new cats onto the cat maze. Yeah, you can use the back of any cat. No, because it has holes in it. Cats don't have holes. Wrong genus. All right, so you all think there's no path? It's the chocolate problem? Uh, oh yeah. Yeah, this is why I have a bag of candy in my office. Yeah, so I bet somebody kind of. I said, "Oh, okay, anyone want to bet money that there's a path or not?" Then somebody said yes, to my surprise. Like if somebody offers you to make a bet, just don't take it. Like they wouldn't offer like, okay. Uh yeah, so but does anyone want to bet? Anyway, so this student lost a bet, and I said, "I don't want your money because you're a student." And then the student came back with this massive bag of candy. Like this joke's on me. Okay. All right, so what can we try to do? Well, we can go like this. So you guys have probably done this much, right? I guess we can go here. This is where you get stuck. Oh, you can go down here. Yeah. Or you can go here. Yeah. The anti-cat cat. Yeah. Okay. So from here, yeah, now it's not so hard. Look at this thing. It has ears, it has a tail, it has 4 feet. Well, it'll have the same genus, but clearly, like you've never met a cat that looked like this. Okay. Don't be bitter that you got tricked. Okay. So that's that. Okay. So the defining thing about breadth first search, depth first search is that you mark the vertices. It's very easy because you mark the vertices, so you don't revisit a vertex, right? So it takes m plus n space. Okay. And believe it or not, there's people out there who ask, do you really need breadcrumbs to solve this problem? Okay. So it's a space complexity problem. So, okay. Oh, I was supposed to leave this blank, and then we were supposed to have a vote. Well, that's okay. Um, okay, so the question is, how much space do you need to solve connectivity? So linear space is, of course, enough, because of breadth first search, depth first search is only using that much space. Can you do polylog n space? You can use something called Savage's theorem, which you might have learned in complexity class. Anyone in complexity class right now? Aren't you? But maybe you haven't done Savage's? Okay. So Savage's theorem is like you try to guess the middle point. Okay. So you say, oh, can I get from point A to point B? And then in n steps or something. Because you can guess number of steps. So let's say you know it's n or something, right? And then you say, okay, can I choose a middle point? You'll try all middle points and say, okay, can I get from here to here in n over 2 steps and here to here in n over 2 steps? And then you'll recurse. But the nice thing is that the recursive stack only goes down one possible trail at a time. So the recursive stack only has log n indices. But each one is doing a loop over all n vertices, so it needs a counter. So you end up only needing log square n space for this incredibly slow algorithm. Okay, but that's called Savage's theorem. Okay. Can you do better than that? Can you do log n? Log n's a clear lower bound because you just need log n bits to remember the name of the n vertices. Okay, so similar number from 1 to n. Okay, and that's what we're going to show today, that you can do it in log n space, or maybe today and Friday. Okay, and we're going to do it randomly because it's a randomized algorithms class. Uh, so after you can do it randomly, the next big question is, did you need to do it randomly? Okay. So later, we'll show how to do it even without randomization. That'll be maybe one of the more exciting things we get to in the class. Okay, so that was a very big open problem because I think log n space had been known for a pretty long time, maybe at least 40, 50, but maybe it's something that was known earlier because it's sort of a clean mathematical thing. Mathematicians would not have asked whether you can do it deterministically, right? So this was an open problem only resolved like 20 years ago. So the question is, how much space do you need to solve connectivity? We'll do log n randomized today, and we'll try to do log n deterministic by the end of the semester. Okay. Does anyone want to guess? Does anyone want to propose some algorithms for this problem? Yeah. Take a random walk. So I'll just start at S and I'll randomly walk around. Okay. Any other ideas? Okay, fine. So we are going to study random walks. Okay. So I just want to know if S and T are connected on directed graph. Start at S, walk around for a polynomial number of steps. If you ever visit T, answer I found it. It's connected. Okay. And then hopefully after logging trials, if they are connected, you'll find a way. You won't even remember the path to get there. But it's okay. So that's the algorithm we'll analyze, right? This is an absurd algorithm. Yeah. Well, you would need memory. Yeah. Well, because O of n, we could always use breadth first search. Yeah, log n. Yeah, so this is, but it's pretty amazing, right? That you can do anything in log n that's non-trivial, right? Um, okay, good, good. Obviously the graph can have cycles. We have all the problems that come up when we introduce breadth first search, depth first search in an algorithms class. Still, somehow, we don't need to mark the vertices. Undirected, yeah. Directed is a major open problem. Like the major open problem, probably in this area. So Savage's theorem will work, I think, on directed graphs. The thing I described where you deterministically guess the middle point. We don't know how to do log n. And as usual, it's very hard to prove a lower bound. We don't know how to prove that you can't do log n in a directed graph, even though that would seem impossible. Deterministic or randomized. But somehow it's always very hard to articulate lower bounds. I mean, it seems like we get one lower bound and you get a whole family nearby things, but people have tried the existing things and what's nearby. It seems like this is somehow different. Okay. Okay, so we're going to talk about random walks. So we're going to have some terminology, new terminology. So one is called the hitting time. So this is if you do a random walk starting at S, what's the expected amount of time until you reach T? I think we'll find out. Yeah, expected number of steps until a random walk from S reaches T. Okay. And the cover time. Anyone want to guess what the cover time is? Yeah, until you cover the whole graph. So how long do you need to walk around until random walk from S visits everyone? It's an undirected graph, so you don't have to worry about getting stuck in a leaf or something like this. Okay, good. So actually the real theorem is that if the graph is connected for any vertex, the cover time is at most m times n minus 1. Yeah, so you'll visit all the vertices that you can within those steps. Good, good. So, okay, something completely different. All right, so the other part of the title was electricity. So, so, so electrical network is just going to be a graph, an undirected graph, okay? And you take a battery and basically a current is like flow. So you sort of inject like 1 unit of flow at S and you take 1 unit of flow out from T. Okay, so electricity flows. That's an okay analogy. But the electricity will take the unit flow going from S to T will take the path of least resistance. That's the terminology in physics. Does anyone know what the path of least resistance is? What would we think it is? When we usually do like graph algorithms, what's the most common? Shortest path, right? That's like what we would do. But that's not what physics does, because physics doesn't do like combinatorics. So for physics, the path of least resistance is defined differently. Sorry? What's kind of like all of them? So so there is a fixed, the electrical flow is actually going to be a fixed thing. Yeah, but how does it determine its spread? Sorry? Okay. Maybe you guys know physics better than me. So let me at least talk about the simple version. Okay, so all right, the flow of least resistance is supposed to be somewhere around here. Ah, okay. So first I'm going to give each edge some resistance value. They're like edge weights. You can assume they're all 1, for example, like in that picture. So when you have a unit flow from S to T, the resistance is going to be like this. The energy is going to be summing over all the edges, the amount of flow on that edge squared. Okay, so electricity tries to minimize the sum of squares, okay, with kind of coefficients given by the resistances. Okay. And so the electrical flow is the unique unit flow from S to T of least electrical energy. That is my understanding of electricity. And so that means here, you don't actually want to, say choose the shortest path and just send one unit of flow. Because if you're minimizing sum of squares, if you can split it up fractionally, right? Like 0.5 squared is 0.25. So you can get it smaller and smaller by splitting things up. So maybe you would you split it up initially 0.25, 0.25, 0.25, and you want to make it somewhat diffuse over all the edges because each time you get a smaller number, the square will make it even smaller. Okay, so you will get something that looks like it's spread out. Here's like an example. It is an ST flow, but it's not necessarily the electrical flow because, yeah, I mean, I just made up numbers. But the same idea though of the flow wanting to be dispersive. But I think if you look carefully, like at every vertex, the flow is conserved. What goes in is what goes out. But it's really trying to disperse it as much as possible. So that is how electrical flow works. Okay. So I think what's interesting about electrical flow is that it's a simple solution to an optimization problem. Minimizing a sum of squares over ST flows. It sounds like exactly the kind of thing we would love to do, right? So and so what we're going to do is we're just going to study what does it mean to optimize this problem, right? In particular, what are the first order conditions? And out it's going to come out all these, famous laws about electricity. So let me just set up some notation. So to define our flows, the input graph is undirected, but we'll just orient the edges arbitrarily. And I'll use positive numbers to say, oh, positive flow, flow in the direction of the edge, negative numbers for opposite direction. So when you're summing squares, of course, it doesn't matter which orientation you choose. It just needs to be consistent. And, okay, so now I want to point out that the flow constraints are a linear system, right? Because you have some flow and you want to make sure that what goes in is what goes out at each vertex. So you just add in the flow going in and you subtract out the flow going out, right? If you take two flows and add it up, the net flow at each vertex are just going to sum up, right? If I multiply the flow by 2, all the net flow values at each vertex are going to go up by 2. So just a linear function. Okay. Of course, you can write it out explicitly, but I guess I didn't. Okay, so that already tells you there's some matrix where BF will take a flow F and map it to the excess flow at each vertex. Okay. So oops. Okay, so yeah. And okay, so what we want is I want my flow, when I put it into my linear function where I just evaluate the net flow, I want it to be 1 unit of flow out of S, 1 unit of flow into T. Okay, so I want BF equals D, where D is this vector. Now, D could be any other vector. So sometimes you have more than one source and one sink. Okay, so in general, these could be arbitrary values over vertices, but they need to sum to 0. the total source amount of flow going in needs to match the total flow going out. Okay, so I guess we can keep focusing on ST just for the sake of concreteness, but everything we do will not care as long as D sums to zero. Yeah. Oh, okay. So I guess I haven't done it yet, but we're looking for a flow F that is sending one unit of flow out of S and one unit of flow into T. Okay. And if I look at a flow and I look at a vertex and say, okay, what's the total amount of flow going in and the amount of flow going minus the amount of flow going out? So that's the net flow at this vertex. That's going to be a linear function of F. If you take F1 and F2 and you add them up, yeah, this thing will sum up too. Okay. So I'm letting B be this linear function. So B takes a unit flow and just outputs for each vector what's the excess with respect to the flow. So here I'm saying, okay, I want S to have one flow leaving. So I guess here BF is really net flow going out of each vertex opposed to net flow going in. So I want one unit of flow to leave S. I want one unit of flow to enter T. And everywhere else, I want to conserve flow, just like ST flow. This is a linear function. Or you can write it down as a linear function. We haven't really made any real observations. We're just giving things, notation. Yeah. Yeah. So this is just, so what I want to do is I want to set up like a convex minimization problem, minimizing a sum of squares subject to linear constraints. And then that's going to be very useful for us in just a moment. Because the math will give us things for free once we're in that form. So in flow, we have undirected edges. So I can send flow this way, I can send flow that way. And I want to represent my flow with a vector, right? I just want to assign values to the edges. So for each edge, I'm just going to pick one of the two possible directions. Say I point it this way. And say if I assign a positive value to this edge, I think of that as like 10 units of flow this way. If I send negative value to the edge, I think of that as 10 units of flow that way. So it's just a notation system. But this way, now it starts to look like some, relatively natural linear algebra or convex optimization problem. So, right. So this formulation, right, it doesn't even look that combinatorial anymore. Minimizing the sum of squares, weighted by resistances, over all vectors F that satisfy this linear system. Bunch of equalities, which are just the net flows. We haven't really made any real observations yet. We're just re-encoding it. Yeah. Yeah. So B will. So if we wanted to do it, so this is already a functional definition. If you're really concerned in the entries of B, then you have some matrix B, and the rows are vertices. Okay, and depending on which edges are pointing at V and which edges aren't in your underlying orientation, you'll have like a 1 if it's pointed in, and a -1 if it's pointed away. Right? So then if you have some flow on an edge, it's going to go down here and say, oh, that's the flow on this edge is going into V, so I'll just add it to V, the V value. Yeah, so it's going to be like, explicitly be like BVU is equal to 1 if in the oriented version E is equal to UV for some vertex V, like it's going in. Yeah, I might have it backwards. Maybe it should be -1. It doesn't matter too much. And -1 if E is pointed out, and then 0 otherwise. So if I have some flow vector, right, and I pass it into B, and I'm looking at the road just for V, it's just going to add up all the edges that are going into V and the edges that are leaving V. Yeah. But, this you can actually just focus on this definition and then just say to yourself, oh, it's linear. There exists some matrix. And then for me, at least personally, then I can kind of keep focusing on the combinatorial or like, the things that are more intuitive to me instead of ones and zeros, which you have to do on paper. Some of them. Okay, so if you're in this situation, right, electrical flow is no longer like a mystical physical thing, right? It's just a simple solution to a simple problem, right? And we encounter these kinds of problems all the time, and we can just study what the problem already tells us. Okay? We don't have to think about particles of electricity anymore. So, okay, so we need a lemma. Okay, so, and you probably recognize this. You may have seen it in some kind of class before. But I'm looking at some kind of convex optimization problem, right? Minimize f of x subject to ax equal b. Now, normally, if there's no ax equals b, you're just minimizing f of x and f is convex, right? How do I know if x is an optimum solution? The gradient is 0, right? That's our usual first order condition. Okay? You can't improve. You're at the bottom of some kind of bowl because of convexity, which is very nice, right? Many problems you don't know if you have an optimum solution, but if it's convex, you actually do. That's kind of unique. Okay, now what happens if you're doing minimizing f of x subject to ax equal b, right? So if I was just minimizing sum of squares, that would be really easy for us. And also the answer would just be 0, right? But we know everything about it. The only thing that's making it a little bit more confusing is this bf equals d, the flow constraints. So we just need to, augment our tools a bit. So the claim is that when you're doing minimizing f of x subject to ax equals b, okay, and you're doing a convex f, now all you know is that the gradient is in the image of the transpose. So you know that f prime of x at the optimum solution is equal to a transpose y for some y. That's the claim. And this is very general. There's nothing to do with electricity in particular, right? I'm sure half the classes maybe encountered this in their research. Maybe not, I don't know. But some, right? Sometimes these are called Kruskun-Tucker or something, I don't know, to be honest. I never know the name of things. So, okay. So to prove this, we need a little bit of linear algebra background or terminology. Okay, it's not too bad. It's just that maybe it's using some things we don't use often. So I want to give 3 definitions. Okay, for any function a, you can define this. Okay, so the kernel is all the points that map to 0. That always includes the vector 0, but include more, right? If you're going from a big dimension to a small dimension, you have a lot of vectors mapping to 0 just from Pigeonhole. Okay. In fact, each of these are actually going to be a subspace, right? In the sense that if I have 2 vectors, x plus y, x and y, they both map to 0, a of x and a of y is 0, because a is linear, a of x plus y is ax plus ay, that's again 0, right? So the kernel is a subspace, that's very nice. The image is all the things that could be output by a. This is also a subspace. Okay. And the co-image is the subspace orthogonal to the kernel. Okay, so at some level, you can imagine, I try to draw it as a picture. You have the entire domain, okay? And you have this kernel, which is some subspace, right? And you say, what are all the vectors orthogonal to the kernel? And I'll give you another subspace. Okay, and they'll actually kind of together, if you give me one vector from here, one vector from here, you get a unique point in the entire space. Okay. Now, in general, A is not a one-to-one mapping, right? If it has a non-empty kernel, it's not a bijection. It's going from a bigger space to a smaller space. But the co-image is always going to be a bijection, because if I have 2 points, uh, x plus y that maps to the same place, uh, why is it? Yeah, okay, let me not worry about it. Okay, so this is always going to be, right, okay. Okay, that's right. So when we talk about the subspace orthogonal to kernel A, it's also sort of like all the vectors are taking modulo A. Okay. So if the difference between two vectors x and y is another point, is a point in A, then they represent the same point in the coimage. So so in this subspace, um, yeah, well, you'll get a bijection. Yeah, yeah, I think that's what comes next. No, yes. Wait, let me just check. Yeah, that's right. Okay. So A transpose is going to actually give you an opposite mapping, but not necessarily an inverse mapping. Okay. And something like this. So this is all we need. I won't prove it, but it's not too bad. Okay. So given this fact, uh, uh, which I don't know. Actually, yeah, I don't know how many people have taken. How many people have seen this in a linear algebra class? Or like, does this seem familiar? Maybe it has been a while. Oh yeah, quotient graphs. Okay. So at least, okay, at least it's not too crazy. Okay, so, all right, the first claim is that the gradient is going to be orthogonal to the kernel of A. Oh, it should be F. Phi is what F is called in the lecture notes that I was sort of absentmindedly looking at. Okay. All right, the first claim is that the gradient needs to be orthogonal to the kernel. So if I have a point X, it satisfies AX equals B, and it's really the minimum over everything such that AX equals B. Then I'm saying the gradient f prime of x needs to be orthogonal to the kernel. Why? Yeah. Yeah, okay, so let's put it this way. So suppose not. So suppose AZ is equal to 0 and f prime of z, no, f prime of x and z is not 0, right? If it wasn't orthogonal to the kernel, there's some point in the kernel. Now what? Yeah, so maybe without loss of generality, this is greater than 0, right? So, and f is continuous or something, right? So if you go in a small direction, so if you went from x and you went slightly in the direction of z, f will go up. But derivative will also say if you go in the opposite direction of z, it'll go down. Okay. So for some very small delta, you know, uh, f of x minus delta z. So if you take the limit of delta down to 0, uh, you know, just calculus tells us, okay, this is x minus delta f prime x of z, right? So if you take a really small step, you can decrease your objective a little bit. Okay. Now, but you're going to still be feasible because AZ is equal to 0, right? So you also have, so this is less than f of x, and you also have a of x minus delta z is equal to a of x, which is equal to b. So you still have a feasible point, right? So the points in the kernel are the directions you can move without violating anything, basically. It's all it's saying. So if you have any, projection with the gradient, you should be able to make a little progress. So if you're optimum, that won't happen. Okay. Fine? Good. So if that's true, now how do we get this theorem? Or this lemma, the original lemma? Again, this phi is an f. There's a star here. Co-image for some y in the range. Okay. Okay. So yeah, a little tedious, but this is something that you get for free just by knowing you're minimizing a convex function subject to linear constraints, right? Nothing to do with electricity in particular. So, okay, okay, so that back to this point, let's apply this to electrical flow and see what happens, right? Okay, all right, so the claim is that, okay, so let F be some feasible flow, right? My claim is that F is an electrical flow if and only if F is R to the minus 1 B transpose P for some P. F is optimal if and only if there exists some P. This is very nice, right? Because it says there's a certificate of optimality. P gives you a certificate. But why? Yeah. Yes, yes, yes. The electrical flow refers to the optimum flow. Yeah, right? So it's a little confusing because I've used F unfortunately, but we're minimizing some function of our flow vector. F again was a poor choice of letter. And our linear constraint was B, right? So our problem was BF equals D, minimizing this thing. So let me use phi. So phi of F is 1/2 sum over E resistance FE squared, right? And subject to BF is equal to D. Okay. So the optimum tells the first order conditions tells us that this gradient, right, is in the image of B transpose. I guess I'll use P, given that's what we're proving. P is actually one value per vertex because V originally mapped edges to vertices, and now B transpose will go backwards. Okay. And now what's the derivative of our objective function? Oh, did I not explain what capital R is? No. Uh, R will be the diagonal matrix of resistances. All these edges. Yeah, okay. That's probably a useful context. So what is the derivative of our objective function? Yeah, so for what it's worth, you could have written our objective like this. So, I mean, that's just change of notation is going to be RF. You can see that here, right? So if you take the derivative with respect to the FEs, the squared is going to drop down. Um, so all that gives you RF is equal to B transpose P. And now you just flip R over. Okay. All right, so let me explain why we did this. Oh, okay, I guess we need to do the converse direction. We don't have time. Okay, so we'll do that next time. But let me explain maybe the punchline because I feel like otherwise it's a little unsatisfying. So we will show the opposite direction next time, which is not too bad. You just plug it in and it's okay. But what you get out of this is Ohm's law, right? So you might have heard of this before. So there is a name for this called electrical potentials, okay? And so you have this Ohm's law where the electrical potentials are always connected to the electrical flow. Okay. But what's so cool about this is when I read the Wikipedia article, it just felt like it was just given to me, this law, but actually it's just the first order conditions of this minimization problem. It's not that mysterious. I didn't personally know that. Okay. So, okay, so we're making progress, and I guess what we'll do next time is, yeah, so we'll keep doing this. So we'll keep plugging away a little bit, and then we'll come back to random walks, and we'll make use of this. So there's going to be an interesting connection between electrical networks and random walks and graphs, and actually between these vertex potentials in particular. And that's going to eventually get us this miraculous result that you will cover the entire graph. Okay? All right, thank you. Okay, well, let me remind us what we're doing. So we're studying the connectivity problem, which you all know, even if you couldn't solve this. Um, but the question is not whether S and T are connected, but can you figure out if S and T are connected in polylogarithmic space or even logarithmic space? And so what we're doing is log n space, and it turns out the algorithm is take a random walk. Just start as T and start at S. Just start walking around. If you reach T, then of course you can reach T. If not, I don't know. And but we need to analyze this. So two terminologies we're going to come back to: hitting time, the expected time if I start from T to get to T, start from S to get from T. Second time, same mistake. Cover time. If I start at S, how long does it take to cover the whole graph? Yeah. 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 So if you don't find T, you might have gotten unlucky. So we'll try again. Yeah. So I'm just going to start the algorithm over. So it'll take like mn log n total steps divided up over log n independent random walks. So what we're going to show is that with constant probability, you'll reach T in one of those if they were connected. But you're not guaranteed to reach T. The log n space is just to do a random walk, you need to know what vertex you're on. There's n vertices, so you need log n bits to write down the name of the vertex. That's it. Otherwise, you assume you can just read the graph. Like you can, just say, oh, give me a neighbor. Oh yeah, probably you also want to keep track of how many steps you've taken. Yeah. Okay. So, um, so in fact, what we are going to prove is that the cover time is always at most mn minus one. Okay. But we took this surprising detour through electrical flow, which, if you recall, you kind of put one unit of flow into S, you're taking one unit of flow out of T. And unlike, max flow or shortest path, uh, electrical flow is going to be the unit flow that minimizes sum of squares. Okay, that's what they call path of least resistance, which I guess is paths, whatever the plural is. So this is going to diffuse the flow over all the edges. You want lots of small amounts of flow over many edges, so that the squaring really decreases the total energy. And um, yeah, so we were setting this up as a linear algebra problem where we fixed an orientation of the edges and just represented a flow as assigning numbers to the edges. Positive numbers in the direction of the orientation, negative numbers in the opposite direction. And and the constraints itself, saying, oh, you need one net flow into T, one net flow out of S, is just a linear function of this vector. Okay, it's a very simple one too. But structurally, we just need the fact that it's linear, because then, what was first presented as a combinatorial kind of physics-y, special problem, is in fact like a very standard type of convex minimization problem. I'm minimizing a sum of squared subject to linear constraints, right? Nothing to do with physics, but just from the form of the problem, you can look at the first order conditions, okay? And the first order conditions say, oh, whenever I'm minimizing a convex F subject to linear constraints, the gradient is always going to be in the image of the transpose of A. Basically because otherwise, if it wasn't, then you'll be able to move in the kernel of A, right? And decrease, based on the gradient. Okay, so you can't have that at the minimum, so that's all that's happening. And okay, so I think sometimes I imagine, okay, what happens if like we just assume math is easy? We knew all the math things. What do you get for free, and what are the ideas left over? So this is an ideal we get for free, just from like a standard math, right? It has nothing to do with any of the characteristics uh, of the problem. So okay, so when we apply this to electrical flow, right? Then the first order conditions are going to read off as follows. Where we needed a converse direction, which I could have done on the lemma stage too, but I guess we'll just do it here. So the claim is that F is an electrical flow if and only if there's a vector P. They're called vertex potentials in the context of electrical flow, such that F is equal to R minus 1, where R is a diagonal. Is that from your point of view? Is that the diagonal or is that the diagonal? Diagonal matrix of resistances, okay? And B transpose, I mean, we're transposing the vector that went from from flows to net flows at vertices. So transpose is going to go from vertices to edges. Okay. And so the first direction, if F is an electrical flow, if it's the optimum solution for this optimization problem, then P exists. That's coming from our lemma. So our convex function is the sum of squares. I take the derivative, I get R times F, big R, and then we just invert it. So that comes for free. And what we didn't have time to do last time was the converse direction. So suppose the flow was of this form. It was equal to R minus 1 VTP for some vector P. Okay. So the claim is that F must be the electrical flow. Okay. Let me make sure I don't mess up. Anyone have an idea for how to prove this? No, I'm trying to say that if F routes D, that's given. But if you have a point P for which F is equal to, this function of P, then F is the optimum flow. It's the electrical flow. Yeah. Yeah. Uh, or let's say, suppose not. So maybe there's some other flow G. Maybe if we can just compare F to G and show that F always has smaller value, so G will also route the flow. Okay. So, okay. So I'm interested in this quantity, GRG minus FRF. I mean, that's just writing our objective in this compact notation. Okay. Now, let's see. Um, yeah, the objective of G minus the objective of F. Okay. Now, uh, this function is convex. Our function as a function of F or function of G is convex, right? So if I look at the difference, it's going to be greater than than like the gradient uh, times the distance from F. So the gradient uh, of this, uh, okay, so that's the gradient, 2 times R. And then I'm going this distance, G minus F. Okay. Now, oh, sorry, so this is greater than equal to by convexity. All right, now what? We haven't used any of our properties yet, our conditions. Yeah, we plug in this F. So R's will cancel. Okay, so I plugged in F is equal to R minus 1 B transpose P, but the R and the R minus 1 canceled out with each other. Sorry? Yeah, sure is a factor of 2. Okay, what next? Yeah. Okay, so let me take it a little more slowly. That's absolutely right, but let me take a piecemeal. So I'm going to transpose B over, which is like, I feel like what we always do. Okay. And what was pointed out is that, well, they both route D, right? And B is saying, okay, given the flow, what's it routing? So BG is equal to D, BF is equal to D, so you get D minus D. So, yeah, right? It's kind of neat to just see it play out, right? As soon as you find this P, uh, you know you have the solution, right? So this is very nice. Okay, so electrical flows are actually very well behaved mathematically. Maybe that's to be expected since it's a basic object in physics. But yeah, for me who has no actual physics intuition, but I can do some math, this makes actually more sense to me. Okay, so so as mentioned last time, this special vector P, they're called electric potentials. Okay. Um, yeah, and that's Ohm's law. Ohm's law says that there's something called electrical potentials and they're related like this. Okay, good job. We did Ohm's law. So now I'm going to introduce something called the Laplacian, which looks a lot like Ohm's law because the last 2 terms are kind of from Ohm's law, right? So let me give, we're going to actually reintroduce it again next class, but what did I hide here? Okay, so, right, right. So, okay, so let me look at this matrix L that for the moment just defined as B, R inverse, B transpose. It's going to be n by n matrix or v times v matrix. Okay, and to build some intuition, suppose I have two vectors. I have a vector x which has values over vertices, so they look like vertex potentials. Okay. If I expand out, you get something like this. Okay. And hope I have something written. Okay, so this can at least be interpreted a little bit more combinatorially. Okay, summing over all edges, 1 over the resistance times this B transpose X for every edge. I'm just reading off the meaning of the vertices. And now what B transpose is remember, so B originally had columns for every edge, okay, and rows for every vertex. Because it takes in a flow and it outputs the demand flow. And if you look at a column, it's going to be an edge. It has two endpoints, like from point A to point B. Kind of a -1 in A and a 1 in B. Okay, so that column for an edge, right? It's really saying, okay, here's these vertex potentials applied kind of to the rows of B or to the rows of B. I don't know. And then now, what is the two columns? That should be squared, in case anyone was looking at me weird for this reason. And I'm going to take the two values at the endpoints and square it, because that's where there's a 1 and a -1 for the edge. Okay? So you get something like this. You're summing over all the edges, and you're taking the difference squared, divided by the resistance. Okay? So this is called, sometimes 1 over RE is called the conductance of an edge, because I guess that's the antonym of resistance. So, okay, there's this thing called the Laplacian. Okay? Okay, so this starts to look very similar to the original objective. So some differences, well, okay, this is on the face different because the objective was looking at vectors on the edges, right? And squaring it, and then it was times resistance instead of divided by resistance. I think we're on the same page. So let's see what I've written. Okay, but first to interpret this, okay, so I want to suggest that this Laplacian has some combinatorial meaning, and for example, you can use it to express cuts of a graph with edge weights given by 1 over RE. Okay, so for example, let's take a set of vertices S. That's one side of the cut. V minus S will be the other side of the cut, right? And look at the vector where I put 1 if it's in S and 0 otherwise, right? So, or I guess you can do it this way, the same difference. Okay. So 1 or -1, depending on whether it's in S or not in S, divided by 2. All right, so if I look at this, right, and I plug into the original formula, whenever I have two vertices on the same side, you're just going to get 1/2 minus 1/2, or -1/2 minus -1/2, same thing, right? You get 0. So all that's left are the edges in the cut. Okay. So this Laplacian of a graph actually has a lot of combinatorial meaning as well. You can recover the weights of all the cuts in the graph, for example, if you're just given the Laplacian. Okay. Yeah. Sorry. Okay. So good. All right. So having introduced that, I think this is your point from before. Right. Okay. I don't think I defined what effective resistance is, did I? That's fine. So given a demand D, I think the value of the electrical flow, the actual energy, I think that's the effective resistance. We'll see if I'm right. I can double check my notes and hope they're right. Sorry. Yeah, yeah. Okay, so the objective value is called effective resistance in this field. Okay. Yeah, it's the electrical energy of the electrical flow. It's the opt value. Yeah, the optimum value, not the optimum. Yeah. Yeah, yeah. So this is right, right, right. So maybe one way to interpret the value is like if there was a single edge, what would the resistance need to be to pay the same, something like this. I don't know. Yeah. Okay. But as far as I'm concerned, it just refers to the opt value. So the real claim is that the opt value is equal to d L inverse d. Okay. So this is like a closed form solution for our earlier convex. D is the demand. So it could be the unit demands 1s minus 1t, 1 at s and 1 at t, negative 1 at t. Or it could be any demands that just sum to zero, where you have multiple sources and multiple sinks, but they all have to sum to zero because what goes in has to be what goes out. Okay. Um, good, good. Uh, I know we're going to eventually get back to random walks. I promise. But we're just going to study electrical networks a little bit more, and we're going to get a better feel for them. And then the random walk thing is going to come for free. Okay. So, okay, let's. Okay, so let's say that let F be electrical flow, right? So that means BF is equal to D, and F is equal to R minus 1 B transpose P for some P, right? Uh, okay, now, okay, so this is what you're pointing out earlier, I think. Let's look at LP, okay, and just expanding out, okay, and this is BF, and this is D. Oh, actually, we don't need this. Okay. What's more interesting is, so the effective resistance is FRF, right? Because F is supposed to be optimum flow, or maybe one half of this, depending on how you define it. So if we expand this out, R minus 1 B transpose P, R, R minus 1 B transpose P, okay? And now I can start canceling out these R's in the middle. Uh, I guess I put the R over there. Yeah, yeah, you're right. R minus 1 B transpose P, okay? R is diagonal, so, uh, and so this thing is PLP, okay? And what's the last step? It's coming from this line here. We plug in P is L inverse D. Okay. Now L inverse, I should be a little bit careful. It's really the pseudo inverse because L is not full rank, right? So that means it's only operating on a certain. There's a subspace for which it is invertible. If you just ignore the things that map to zero. So it's within this subspace you do the inverse, yeah. Which means it continues to be zero for the orthogonal complement. Okay. But for all, you can just think of this as something like an inverse. Okay. It's invertible over the space of vectors that, outside the kernel, orthogonal to the kernel. Okay. So we're always working in that space. Okay. So what's the moral of the story? I guess the moral is, electrical flows are even better behaved, right? There's some matrix L where electrical potential is just dl minus 1d. You're not even doing optimization anymore. Inverting might be a pain. Inverting L might be a pain. But once you have it, you just apply it to D. So what started out as convex optimization or semi-combinatorial, right? Because it's an ST flow. Once you look at the first order conditions and you just push everything through, you're just left with, you're just multiplying a matrix with a vector. Okay. Right. Okay, good. It has everything to do with the operator Laplacian, yeah. We're going to talk about Laplacian a lot for the next couple of weeks, I think. Turns out to be very useful. Okay, so now I think we're going to go back to random walks, okay? Okay, so we have some electrical network tricks under our belt, and now we're going to go back to this exciting question: how do you get from S to T with using a minimum amount of memory? So again, yeah, just some terminology. Okay, so we're going to look at hitting time. We're going to model it as a set of equations. Okay, so what we're going to do is we're going to fix t, and then I'm going to look at the hitting time from other vertices to t. Hitting time is what is the expected number of steps until I get to t. So the first one is not so interesting, just 0. Okay, but now I want to try to write yes. Yeah, so the definition of the precise definition of hitting time will be: imagine you start a random walk at t. What's the expected number of steps until you arrive at t again? So by rule, if you're already at t, it just ends at 0 steps. Yeah, yeah. So then they're not really a walk. It's more interesting, of course, when the first vertex is not t. Say it's some vertex u, and we're not going to be able to just guess it right away. So what I want to do is I want to write hu of t maybe recursively, right? So you're at u and you wonder how many steps it'll take to get to t on average. Yeah. Yeah, so I take one step, I go to a random neighbor, and then from there, how long will it take to get to t on average? Okay, so we're going to do that. We're going to do the average over all the neighbors, right? Okay. Nothing special. Now, here's the crazy part. I'm going to define vertex potentials P by P of u is the hitting time to T. Okay. All right, so, and then look at this flow. Oh, so uh, you can think of it as a vector or a function, but you can think of discrete functions as vectors. So f is mapping vertices to real values is just like if I had written down the values in a vector that are indexed by the vertices, the graph. And so you can this can yeah. So if you prefer the vector notation, then we're looking at the youth index of the vector p. Yeah. Okay. Um, sorry. What did I? Oh, okay. Okay. So we have some kind of flow which is PV minus PU. Okay. And let's see where this goes. So what I've done is I defined some set of vertex potentials. Okay. And now I'm looking at like the corresponding flow. If I interpret the input graph as a graph with no resistances or unit resistance everywhere. In which case the flow will always be the difference between the two endpoints. Okay, so let's see what happens. Okay, so all right, so PU is equal to HUT, right? And so if we just kind of plug this in, um, you get something like this, right? Now, let me just make sure I do this correctly, which is code word for, I should have read this a little more before we started. Okay, so, right, right. All right, now check this out. We are going to, so what I want to do, right, is, is, uh, is I want to take this vertex potential and flow and try to figure out what it's routing, right? If I figure out what it's routing, then since F is equal to B transpose P, it's automatically the best flow for those demands. Okay? So again, the flow on an edge UV is going to be equal to PV minus PU. Okay? So what I want to do is I want to start from here and get something that looks like a bunch of PUs minus PXs or something. So we don't know what we're routing. We have a flow, it routes something. I know that my P was based on this system of equations. And what I'm going to do is I'm going to manipulate the system of equation and out, what comes out is going to look like basically the net flow into U. Yeah. Yeah. From X to T. X to T. So I'm trying to go from U to T, right? How long will it take? I take one step, it takes me to a neighbor, and then from there, how long do I expect it to take? Yeah. Okay, what we're going to do is let me first clear the denominator. Uh, now what? Okay. sum over x in nu pu minus px is equal to the degree of u. Okay, for u not equal to t. Okay. Now this starts to look like net flow stuff, right? So I did this correctly. PUV is PV minus PU, so this should be the sum over all neighbors x of the flow from, I guess, x to u. I'm doing it correctly. U to x. U to V is PV minus VU. PU. So PV minus PU, PU minus PX. Okay, so it's x to u, right? So for every vertex u that's not t, okay, this flow is sending degree u units of flow into t, into u. Sorry. Okay, so the net flow. So that means every vertex except for t is a sink of weight of value degree u equal to its degree. Okay, so P is, or maybe I got the source backwards, something like that. Okay. So P is encoding the flow. I might have flipped source and sink, but that's not a big deal. Okay. Uh, where I'm injecting 4 units of flow into every vertex. Sorry, flow equal to degree, which for the first vertex I looked at was 4. Okay. And then it's subtracting out the rest of the flow from T. Sorry, yeah, so the one in the middle, there's a negative 99. Oh, uh, yes. So maybe, yeah, pick one of them and it'll be negative or something, okay? Then it will, if you sum them up, they'll add up to 0. Okay, so why is that so great? Okay, so here's the next claim. The claim is that the hitting time from U to V plus the hitting time from V to U is exactly 2m times the energy of the unit UV electrical flow. Okay, now things are starting to get crazy because the left-hand side is something about hitting time, and the right-hand side is something about UV electrical flow. Okay, so this is like complete nonsense. Right? Okay, so how do we prove this? Yeah, that's exactly what we'll do. Did I write it out? Nope. I'll have to do it together. Okay, so um, that's a little annoying. Uh, okay, we'll see how this goes. All right, so I'm going to define P to be H. Okay, let me do one thing to be consistent with the notes. I'm going to change this to S and T. Okay, all right, so we're going to define H to be the hitting times to S and Q to be the hitting times uh, to T. Okay, and and I'm going to let R be equal to P minus Q. Okay. Sorry? Oh, yeah, R does not refer, there's no resistances for any of our problems anymore. Yeah. Yeah. So R is just going to be defined differently. It's only chosen because it's the next letter in the alphabet after P and Q. And S and T are taken up ahead. So we're just kind of crammed in the alphabet here. And okay, good. So mhm. Okay, let me just make sure this is correct. Okay, I just have like some random changes of notation of my notes. It's confusing me a little bit. Okay, so if I look at HST plus HTS, this is PU minus PV. Uh, oh yeah, this is where I'm getting confused. Okay, PS minus PT plus QS QT uh, minus QS because why? Okay, okay, that's just because two of them are zero, right? So P PS is zero. Did I get this right? Okay, let's just keep going. Okay, so we'll fix this if we figure out what's going on. So this is RS minus RT, and then we have B transpose R is B transpose P minus B transpose Q. So the flow for R is going to be equal to the flow for P minus the flow for Q, because B transpose P gives me the flow for P for vertex potentials P. The flow for Q gives me, okay. And what the, oh, did I miss? Okay, I see. I should have mentioned, okay. It's okay. Okay, okay. Now, if I look back here, right, uh, the two demands are also going to be added up, the one for S and the one for T, okay? Or it's going to be subtracted, actually. So then what you're going to be left with is that for all the vertices that are not S or T, it's going to have one negative degree U and one positive degree U. They're going to cancel out, okay? And then what you're going to be left with is flow routing 2m units of flow. Okay, so how do I put this? So the bottom, yeah, uh, yeah, that sum shouldn't be there. Okay, I need to check some of the notes. Yeah, notes went wonky at the end. It's messing up me up right now. Okay, okay, what does B transpose P, which corresponds to the hitting times to S route, is going to inject degree units of flow into every vertex except for S and subtract everything out, right? And what does Q route? Q is going to inject degree units of flow to all vertices except for T and takes things out of T. Okay, the corresponding flows, where I take B transpose P, B transpose Q. So now if I look at one flow minus the other, okay, so every vertex except for S and T, you're going to have the same in, same out, is going to cancel out to 0. And then what's left is you're going to be routing 2m units of flow from S to T. Unless I got the signs backwards, in which case it's 2m units of flow from T to S, but it's okay, it's undirected graph. Okay. So so this routes 2m flow from S to T, and it's the electrical flow routing it because it's of the form B transpose R for some R. Okay, so to get the unit flow, you divide it by 2m. Okay, and so you're left with HST plus HTS is equal to R S minus RT, which I can write as RD, where D of S is equal to 1, D of T is equal to -1, and everything else is 0. Okay, so the unit demand from S to T. Okay, good. We're gonna survive this proof. And so right. So this is going to be RB B transpose R. Okay, just plugging in for D because B transpose R is the flow routing D. And that's the yeah, so then you get 1 over 2m B transpose R B transpose R which is 2m times, okay, B transpose R over 2m B transpose R over 2m. Now yeah, and where's, sorry? So I didn't fully explain this. Yeah. Let me go back up here real quick. Sorry, my notes are a bit of a mess, it seems. So this was also we actually have two formulas for, lots of formulas for the effective resistance electrical energy. But another one we stumbled into is PLP, where P was the potentials. Because if you plug in Ohm's law, then you get dl minus 1d. Okay? So this is putting everything together. This is more chaotic than I had in mind. Putting everything together, this is effective resistance from S to T. Okay? So it's going to be 2m times the cost to go from U to V. Okay, we're over time, but we're going to finish. Oh, here's some stuff I set up. Okay. All right. So now, okay. So with all this in mind, now we're going to try to finish off this theorem. Okay. The claim is the cover time is at most 2mn. And this part will be combinatorial and fast and less nonsense. Okay. So, yeah, I had a picture. Okay. Fix a traversal of any spanning tree. Okay, look at a spanning tree in the graph. Okay. Now, the total time to traverse the entire tree exactly in expectation will be HUV plus HVU over all the edges UV. Right? How long does it take from U to U to V, then from V to the next one, to the next one, to the next one? Okay, we're walking around the graph. Okay, that's how long it would take an expectation to traverse that tree. Okay, and what we showed is that this is 2m times the energy of unit UV flows over all of the edges in the spanning tree. Okay. So this we have. Good. Okay. So now what my last question is, for any edge in the graph, what is an upper bound on the electrical flow for any of these UVs? What's an upper bound on the electrical flow? 1. Why? What is an electrical flow that gives you energy 1? We know the best flow is less, right? So what would be a flow that would give you energy 1? Just on that edge, right? Oh, bummer. So this would be 1, because I can just put 1 unit of flow into U and just route it on that edge. It's probably better because you can use other edges, but it's at most 1. Okay? And we go back here, we throw that into the mix, and you somehow end up with 2mn. Okay? So something kind of wild has happened. It would have been more convincing if I was a little bit smoother in some of those proofs, of course. But at some level, we started with what's the hitting cover time for the entire graph. And we turned it into what's the sum of unit electrical flows over all the edges in a spanning tree, right? So one thing extremely valuable is that HVUV plus HVU is 2m times the energy of a unit flow, okay? And that somehow comes all the way back to if I take these hitting times and I use them and if I define vertex potentials based on the hitting times, right? Then actually the linear system solved by the hitting times will show me the demands of the corresponding flow. Okay. And yeah, and it just works. Okay. So yeah. Yeah. That's right. That's right. Well, so the algorithm doesn't need to know the hitting time, right? So it's just mathematically the hitting time is some value out there. It is a concrete fixed thing. And we use that as inspiration to define vertex potentials. And then we looked at the flow, and it turns out that you can kind of read off from the linear equation solved by the hitting times the corresponding flow and what demands they satisfy. And it just everything just works out very, very nicely. Yeah, so any vertex potentials can be turned into a flow vector by doing B transpose P. And it will be the electrical flow for whatever demands it satisfies by Ohm's law, because you already have the potentials P. So we just have to say, okay, what would the demands be? And you just look at it based on those equations. And the nice thing is that you can take the difference of two of these flows and you get an ST kind of demand. Right, so this one is like for that particular vertex T, kind of everything is going into T at some level and everything is going out of everyone else based on their degree. And I can do the same thing for S. And if I do the potential for T minus the potential for F, I'll get the corresponding flow for T minus the flow for S. And the demands for T minus the demands for S, which now looks just like a unit, like a really big ST flow. So with this hitting time trick, we start putting together, we start figuring out what the electrical flow looks like between any two vertices. Yeah. 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 In fact, we didn't even look at all random walks. In the proof, we just fixed, suppose you tried to visit all these vertices in sequence based on some particular spanning tree. Then, from first vertex, second vertex, that's the hitting time from first to second, second to third, fourth to fifth. Eventually go back up, so then you go from second vertex back to first vertex. So you get the HU plus HVU thing that we just showed is really well behaved. Yeah, I agree with that. I agree with that. Yeah, so you could say that's where the random walk entered, or yeah, I mean that all has to do with the random walk being in the definition of HUV as well, because that equation comes from parsing out the definition. So yeah, so this is just an upper bound on any random walk. You say, oh yeah, yeah, remember, but if I instead of worrying about just getting from S to T, or just trying to do, so really we're bounding the cover time. How long does it take for a random walk from S to visit everyone? And that could be much better than, trying to follow this particular tree, right? So this is a very pessimistic upper bound. On the other hand, it's a bound that holds no matter the graph. That's one thing good about this proof, right? Well, the graph needs to be connected. But because if a graph was like a click, like all the edges, then it's going to be you can go everywhere really fast because each step you can visit anyone. But even a very unconnected graph, in which case a spanning tree starts to look like the worst case. Um, yeah, you can start doing things like this. So yeah, so something sort of magical happened. I think what I think is really interesting is the surprising connection between random walks and electrical networks, because that used to be two different worlds. It happens that you can interpret the linear system satisfied by HUV and make this connection and get a useful bound. So I feel like I'm not doing a great job of summarizing. Anyone else is allowed to summarize? But at the very least, hopefully you're like, wow, that was great. That was exciting.